Science is real, from the Big Bang to DNA.
Welcome to Chemical Kinetics, Chapter 12 of our AP Chem textbook. Also, welcome to our first video series. I hope that having some time to watch and review the lectures will give us more time in class to do more activities that allow us to process all this kinetic stuff. All right, so we're going to open with the concept of rates. How fast does it go? In physics, you look at rate when you study motion, as in change in distance over change in time. Classic example, your speedometer, miles per hour, distance per unit time. When studying gases, we examined rates of effusion. We described how fast a gas escapes through a small hole by looking at the amount of gas escaping per minute. Now, we're going to look at reaction rate. We're going to focus on change in concentration, which is denoted by the bracketed substance A, over change in time, seconds, minutes, hours. We're talking about change in concentration. That's a very specific view of the reaction. Let's recall we describe concentration quantitatively by looking at molarity, molality, mass percent, and mole fraction. These are all ways of describing the particles of solute relative to the amount of solvent or solution as a whole. For consistency's sake, chemists choose to use molarity when discussing kinetics. So, when describing how fast a reaction happens, we will look at moles of particles per liter of solution.
Hey, all right, so let's think about that for a second. If I have a solution and I'm reacting with something and the solute particles start to decrease, then it makes sense that the change in concentration would decrease, and as a result you're getting a change in concentration and a rate associated with that based on the amount of time. But what might be less obvious is what happens with a solid or a liquid or a gas. So let's think about it. A solid. If I have a solid and it's a chunk of solid right here, and I start using up those particles, well, does the concentration really change? Well, the answer is no. You see, the purity of the solid remains constant. As particles are being removed to react with something else, the volume also is changing, and therefore the concentration of the pure substance is unchanging. As a result, we can't use that to study rate. Same goes with a liquid. When we have a liquid, if I have a liquid in a container and I start removing some to represent the idea that the liquid itself is leaving and becoming something else, the volume of that liquid, the amount of actual liquid in there, changes along with the number of particles that go. And so as a result, the concentration of the liquid is unchanging as well. So when you're dealing with pure solids and pure liquids, they don't affect the rate because their concentration, their level of purity does not change. However, gas is tricky. Remember, gas takes the volume of its container. So if I have a container so big and I start taking away gas molecules that were in that container before, no problem. The other gas molecules just take up that space. And so there's less particles per the amount of space that we have per unit volume. And so when you're looking at reaction rates and change in concentration, you really can only refer to change in concentration of aqueous solutions and gases, because liquids and solids, they just don't change.
So let's examine a reaction that involves gases. This is a picture of figure 12.1 from your textbook. It shows the rate of decomposition of nitrogen dioxide into nitrogen monoxide and oxygen gases and the balanced equation of the reaction. You see the axes are labeled concentration and time. Notice what happens to the concentration of NO2 over time. It decreases along this curve. As the concentration of NO2 decreases, we also notice that the concentration of NO and O2 increase along these curves. So there are a few important points that are related to this graph. First, notice the changes in concentration aren't happening at a constant rate, as indicated by the curved lines. Just like your GPS will tell you an average speed that you traveled on a road trip, the equation we saw before is actually an average rate. To get the instantaneous rate, you can calculate the slope of a tangent line along the curve at any point. Recall that a tangent is a straight line that touches the curve at one point along the curve. Finding the slope of that line by doing rise over run will give you change in concentration over change in time at that point, or rate. Another thing to notice is that the curves of the products aren't identical, which means they aren't being produced at the same rate. If we look at the stoichiometry of the reaction, this makes total sense. For every 2 NO2s that decompose, they produce 2 NOs for every 1 O2. So twice as many NOs are forming compared to O2. Your textbook sets up the tangents to find the instantaneous rates at the 252nd point for both products. If you do the calculation change in concentration over change in time, or rise over run, you find that the rate of NO2 is twice that of O2. Feel free to pause if you want to check it out. If the stoichiometry holds true for the products, it holds true for the rate of the reactants at the same time too, in theory. Notice that we are decreasing the concentration of the reactant, so we include a negative sign to truly make the values equivalent. This brings us to the last important point this graph leads us. Look carefully at the shapes of the curves. If I were to continue plotting the data for these reactions for a greater period of time, what would those curves look like? Take a moment to envision it in your head. All right, well, let me go ahead and show you now. There we go. Eventually, they would become straight lines. There's no more change in concentration. But notice it isn't the case that all the NO2 has been used up. There's still a concentration value for it. The issue isn't that it's all been used up, it's that the system has reached equilibrium. And once it reaches equilibrium, there's no change in concentration. So there's no rate of reaction, at least that we can measure. Recall from honors chemistry that at equilibrium, the forward reaction happens at the same rate as the reverse of the reaction. So in the green section of the screen, where the lines straighten out, the reverse reaction is happening as fast as the forward reaction. That leads me to our next point. Reactions are reversible. In fact, most reactions are reversible. If at the point of equilibrium the rate of the reversible reaction equals that of the forward reaction, it makes sense that there's some kind of reversible reaction that occurs before that point. Look at the curves. They start out with much sharper slopes early in the reaction. That is because the amount of reverse reaction is negligible. For this reason, chemists choose to focus on this initial portion of the reaction when studying the kinetics reaction, because it's the most accurate representation of the rate of the forward reaction. If this is the case, then we can also be a little more consistent on which rates we actually choose to focus: the products or the reactants. We saw before that they are all related by their stoichiometry, but if we're looking at the beginning of a reaction to minimize the effects of reverse reactions, the clear choice is to focus on the reactants. So our rate equation becomes rate equals negative change in concentration of reactant A over change in time. Again, the negative is because the change in concentration will be decreasing and rates are positive values.
Hey, Mom! Why do we care about weights?
Good question. Why do we care how fast or slow a reaction happens? Well, how fast or slow a reaction happens is indicative of its mechanism, or steps the molecules take to complete a reaction. Once you know the steps the molecules are taking, you can do things to help make them happen easier or inhibit them from happening to slow the reaction down. This is really helpful in industry. We'll actually get into this a little bit more when he's gone and we start talking about mechanisms.
Now we really get into the meat and potatoes of our kinetics: rate law. A rate law is a mathematical function that describes the rate of a reaction. It basically looks like this. Remember, we established earlier that we are going to be focusing our kinetics attention at the beginning of the reaction, where the reversible reaction is the most negligible. So when writing rate laws, the concentration will be in terms of any reactants involved. Well, not any, What two types of reactants will we not include? Now, if you said solids and liquids, you'd be right. As for the other parts, K is commonly referred to as the rate constant. It basically works as a proportionality constant to allow the concentration units to convert to units of rate. It tries to be a little bit tricky, but we'll deal with that as we're working with our problems in class. N refers to the order of the reactant and ultimately the reaction as a whole. Usually it is the value 0, 1, or 2, but it can be a larger integer and occasionally a fraction. Both K and N must be determined experimentally. Remember that graph we finished talking about? Well, be prepared to look and create a whole lot more of them in class. In the meantime, let's go ahead and write some general rate law equations, just to get us started. Alright, so let's write a rate law. Here we have a reaction. We've got ammonium solution reacting with a nitrite solution to produce nitrogen gas and liquid water. We know from our previous equation that I showed you that we're going to be looking at the reactant side only, because that is where we can examine the forward reaction most effectively. We're writing a general form of the rate law, so let's do it. We start with rate equals K. Remember, K is the rate constant. It's a proportionality constant. It must be determined experimentally, so for right now, it's just going to stay K. We write a bracket and we write our first reactant, which is NH4. And we're going to raise that to the order of the reactant. We don't know what that is, because again, that must be determined experimentally, so we're going to give it the variable N. Then we have another reactant in this case, so NO2, negative, which we'll raise to the M. And there you go. You have your general form of the rate law, focusing on the reactants and taking into account the concentrations of each of those, as well as the order of the reaction, which we'll get to next. All right, let's try another one. For this rate law, the equation's a little more complicated. However, if we stick with our same rules, you'll see the rate law itself looks basically the same as the one we did before. We're going to start with rate equals, and again, K, the proportionality constant. We don't have a value right now. We'll stick with K. And now we're going to look at which reactants we're actually going to consider. Remember our rules. We're looking at change in concentration. And so if concentration isn't going to change or doesn't matter, we're not going to consider that. So that ethanol on the end over there, yeah, we're just going to ignore it. Instead, we're only going to conclude the aqueous solutions and gaseous reactants. We've got H+, and we're going to raise that to the N. Then we have our dichromate, and we're going to raise that to the M. We're not going to include the ethanol again because it's considered a pure liquid, and that doesn't change its concentration in the process. So it's not considered in the rate law equation. And there you go. Another general rate law.
So that's it for video number 1. Be sure to come to class with any questions you have. We are going to spend the next few classes actually making sure everybody's clear on creating and interpreting graphs relating to rate, and then using those graphs to determine the order of various reactions. We'll also actually make sure we're all clear on what I even mean by order of a reaction. I guess that's it for now. See you in class.
Science is real.